In this video, we are going to go through the decimal expansion of rational numbers and irrational numbers. So first of all, look at this classification. We know real numbers can be classified into two categories, that is with decimal, the numbers which are having decimal expansions, and without decimal, the number without decimal expansions. Right? Such numbers are called as integers. The examples of that include -3, -2, 0, 1, 2, 3, so on. Right? These are all the integers. Now, in case if they are having decimal expansion, in that case, it can be further classified into two categories. Where first category is the decimal expansion is terminating. The decimal expansion is terminating. Now, what happens over here? The decimal expansion will terminate after a certain point of time. The examples of that would be 0.5. Right? It is terminating after one decimal expansion. So 0.5, then 1.25. These are some of the examples of terminating decimal expansion. Now the other category is non-terminating. Now in non-terminating also we have two subcategories. That the decimal expansion is non-terminating as well as repeating. So we can say the decimal expansion is non-terminating as well as there is some pattern that it is repeating. The examples of that will be, let's say you have 1.23, 23, 23 and so on. These three dots includes that it will not terminate. Right? These three dots means that it will not terminate. So here you can see that 2, 3 is a pattern. It keeps on repeating, right? In this decimal expansion. Same way you can consider 0.545, 545. So this 545, 545 it keeps on repeating, right? So we can consider this decimal expansion as non-terminating and repeating. Now the other classification under non-terminating is non-terminating as well as non-repeating, which means the decimal expansion will neither terminate nor repeat. So we can write it down in the form of, let's say you have 1.234567 and so on. Okay, so in this decimal expansion you can say that it is not terminating, right? It is not terminating after a certain point of time, as well as it is not repeating also. Same way you can consider another example as 0.785769. So here also you can see that there is no pattern over here, right? So 785, 769, there is nothing such as which is repeating. There is no pattern over here which keeps on repeating. So therefore it is called as non-terminating, non-repeating. Now these two categories, terminating decimal expansion and non-terminating repeating decimal expansion, they fall under rational numbers. They fall under rational numbers, which basically means that these numbers can be written in the form of P by Q, where Q is not equals to 0. Now, what about non-terminating, non-repeating decimal expansions? Then such numbers are actually irrational numbers. Such numbers are actually irrational numbers, which means you cannot write it down in the form of P by Q. Okay, you cannot write down irrational numbers in the form of P by Q. So this was the classification of real numbers based on decimal expansions. with decimal. There are two subcategories, terminating as well as non-terminating. In terminating, there are two subcategories, non-terminating repeating and non-terminating non-repeating. Now, terminating decimal expansions and non-terminating repeating decimal expansions, these two fall under the case of rational numbers. Whereas non-terminating non-repeating decimal expansions, they are nothing but irrational numbers. Now, next we are going to go through some theorems. So, Theorem 1.5. Here, let x be a rational number whose decimal expansion terminates. So, we will consider, let's say, x is equals to 0.5. The decimal expansion is terminating, right? Then, x can be written in the form of p by q. They are saying that if it is terminating, if x is terminating, then you can write down this 0.5 in the form of p by q, where p and q are co-primes, which means the HCF of highest common factor of p and q will be 1, and the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So let's try it out. We can write down 0.5 into 10, and in the denominator also we can multiply 10, right? So what are we going to get? We will get 5 by 10. Now, is this simplified? No, we can simplify it further in the form of 1 by 2, right? So here you can see the denominator is 2, right, which can be written in the form of 2 raised to n and 5 raised to m. You can write it down, it's in the form of 1 upon 2 raised to 1 into 5 raised to 0. So this is what this theorem 1.5 is, that if you have a decimal expansion which is terminating, then that number can be written in the form of p by q, where p and q are co-prime. You can observe in 1 by 2, 1 and 2 are co-prime because they are not having any other common factor apart from 1, right? As well as the denominator q will be of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So, if you will compare 2 raised to 1 into 5 raised to 0 with 2 raised to n into 5 raised to m, you can clearly observe that n value is 1 and m value is 0 over here, right? And both of them are non-negative integers. So, this is what this theorem means, Theorem 1.5. Next, we have Theorem 1.6. Here, this theorem says that let x equals to p by q be a rational number. So, let's say x is equals to 1 upon 5. Okay, this is a rational number. So, they are saying that such that prime factorization of q is of the form 2 raised to n into 5 raised to m. Now, the prime factorization of q is what? 5, right? We can write down 5 in the form of 2 raised to 0 into 5 raised to 1, right? Now, if this happens, then this theorem conveys that x has a decimal expansion which will terminate. So, it means that here x will have a decimal expansion which will terminate. Now, we can try it out also. What we can do, in order to find out the decimal expansion without division, what we can do is, we can multiply the numerator and denominator with the same power as 5 is having. So, here we will multiply numerator and denominator with 2. What are we going to get? We will get 2 in the numerator, and in the denominator we will be having 2 raised to 1 into 5 raised to 1. So, 2 into 5 we will get 10, right? So, this can be easily written as 2 upon 10. Now, we know we can easily find out the decimal expansion of this number. It is 0.2. So, what did we observe? That here x was equals to 1 by 5, right? It is in the form of a rational number p by q, where the prime factorization of q is in the form of 2 raised to n and 5 raised to m, where n and m are non-negative integers. Then, in that case, we observed that the decimal expansion of this number terminates. So, now we are at Theorem 1.7. Here you can observe that let x equals to p by q. Let x equals to p by q. where P and Q are co-primes, which means the highest common factor of P and Q will be equals to 1. Be a rational number. We are assuming X to be a rational number which can be written in the form of P by Q, where P and Q are co-primes, such that the prime factorization of Q is not of the form, this is very important, it is not of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. So what are we assuming? Let's say our example is x is equals to 1 by 3. Now you can clearly see the denominator here Q is equals to 3, right? Which is not of the form 2 raised to something and 5 raised to something, right? 2 raised to something into 5 raised to something. This 3 is not of this form, right? The prime factorization of 3 will not be of this form. So what did we understand from this? Then definitely according to this theorem, the decimal expansion of this 1 by 3 will be non-terminating, which means it will not terminate at a certain point of time. It will keep on repeating itself. There will be certain pattern in the decimal expansion which will keep on repeating. So like here you can observe, if you will divide 1 by 3, what are we going to get? We will get 0.3333 and so on, right? These 3 dots indicates that it is not terminating. As well as you can observe that here 3 keeps on repeating, right? 3 is a pattern which keeps on repeating. So therefore, this is the meaning of Theorem 1.7, that if you have a rational number which can be written in the form of P by Q, where P and Q are co-primes, and Q is not of the form, the prime factorization of Q is not of the form 2 raised to something into 5 raised to something, where the exponents of 2 and 5 should be non-negative integers, which means they should be whole numbers. So if you cannot write down the denominator of the rational number in the form of 2 raised to n into 5 raised to m, then that rational number will have a decimal expansion which will be non-terminating and repeating. Repeating is also known as recurring.